Hello. Today, I'm going to present our paper, Planning Epidemic Interventions with EpiPolicy. My name is Zain, and my co-authors are Miro, Xuan, Whitney, Azza, and Dennis. Combating epidemics is a global and an ongoing problem. Humankind has been faced with infectious and deadly diseases since the beginning. When an epidemic emerges in a region, containing its spread becomes the top priority of public health officials. Some recent examples of worldwide epidemics include the 2009 flu pandemic, Ebola, MERS, Zika, and the current COVID-19 pandemic. Modeling epidemics and simulating various intervention scenarios enables policymakers to assess the impact of their policies, allowing them to plan appropriate response strategies. The first step in a model-driven policy response process is building a reasonably predictive disease model. As policies usually target specific segments of a population, such as children, seniors, essential or non-essential workers, the demographic properties of each group have to be defined. This also includes defining the mobility patterns of the population to see how the disease spreads within and among various population groups and geographic regions. Once the model and population are set, the users may define a set of interventions such as masks, social distancing, or vaccinations. After specifying the model, population properties, and interventions, users may run multiple simulations to examine the trajectory of the epidemic. Many simulations may need to be run with different model parameters and intervention effects to arrive at a plan. The results of the simulations are then communicated to the stakeholders. This is an iterative process. The model and interventions are regularly updated to include new information about the epidemic as it becomes available. Common ways of modeling epidemics are by writing code in programming languages such as R or Python. Simulation tools such as STEM, Gleamwith, and tools developed by the Institute of Disease Modeling are also frequently used. However, these tools for modeling epidemics suffer from some or all of the following problems. As the code base or the configuration files of the simulation evolve with the epidemic, they become hard to navigate and manage. Finding and understanding why certain choices were made in different simulations becomes tedious. Making modifications in the existing model and interventions is hard to do, and adding new interventions requires more code to be written. All bookkeeping is also usually done outside the program itself, in the form of emails or spreadsheets, making it difficult to trace the reasons for particular choices. Finally, a lot of additional tools are used in the simulation process, such as spreadsheets to store data, graphing tools for visualization, etc. To make the tasks involved in model-driven policymaking easier, we developed EpiPolicy. We were guided by three main principles while designing EpiPolicy. These are high-level abstractions, separation of concerns, and sufficient and minimal APIs. First, we surfaced three high-level concepts to simplify the process of defining a model. A locale is a geographic region with a population. A locale may have one or more sublocales to model lower-level administrative regions with different population densities, such as cities or villages. A group is a segment of the population for which the disease may behave differently, such as high severity of symptoms for older people with COVID-19, or for which targeted interventions need to be specified, such as students or essential workers. A facility is any place within a locale where people may spend time and interact with each other, such as schools, households, or workplaces. Second, we built EpiPolicy with an interactive graphical user interface with distinct and task-oriented sections that allow users to focus on specific aspects of their model without getting lost in the code. There are helpful visualizations built within EpiPolicy that allow users to visualize and understand their model choices. Furthermore, each data item can be associated with an article, text description, or code repository to trace them back to the original sources. Third, EpiPolicy provides 4 APIs to allow users to define interventions. Instead of writing complex code EpiPolicy's APIs allow users to simply use Python dictionaries and regular expressions to identify the specific components of the simulation that they want to modify, such as the model parameters or population mobility. Users are also able to access the inner state of the simulation to compute intervention parameters dynamically. Here are a few examples of intervention functions specified in EpiPolicy. To learn more about the intervention APIs, I invite you to read our paper. Now, let us see how a user can define a basic SIR model with subpopulation groups and interventions. We will select the SIR model from the list of built-in models. Next, we load geographic and population data for a fictional country. Then, we create 3 subpopulation groups by defining the genders and age ranges of each group. EpiPolicy will automatically calculate the distribution of each group within each locale, using the demographic data loaded in the previous step. After defining the groups, we can load data for facilities and mobility using EpiPolicy's built-in plugins. Once the population data is set, we can now define our interventions. In EpiPolicy, interventions are defined in the form of Python functions using EpiPolicy's APIs. One of our major design decisions while designing the intervention specification method was to separate the specification of the effect of an intervention from when, where, and how intensely it is applied. By extracting these control parameters out of the intervention functions, which are specified in the control parameters table and passed to each intervention function as arguments, EpiPolicy allows users to modify and combine different effects of interventions easily. Here, we define 4 interventions: vaccinations, masks, border closures, and social distancing. In the schedule section, we set the duration of the simulation, the duration of each intervention, as well as the location where the intervention is applied, along with the values of the control parameters. The results page shows interactive visualizations corresponding to each intervention plan to show the effect of each plan as well as the final cost. We elicited user feedback in the form of focus groups, hands-on workshops, and demonstrations. The participants included researchers at a university, a public policy consultancy, an NGO, a team of public health officials, and an AI solutions company. All participants were familiar with common modeling tools. Users found EpiPolicy useful for their modeling tasks, such as modeling different intervention scenarios and different population groups. Teams collaborated well when specifying interventions and constructing schedules. EpiPolicy allowed users to collaboratively discuss aspects of their models and intervention plans instead of focusing on the underlying code. The visual and interactive interface of EpiPolicy enabled users to easily navigate and understand their model and interventions. Thank you for listening to this presentation. Please refer to our website for tutorials and documentation, and don't hesitate to contact us for more information. Thanks.